Simple harmonic motion can take some diverse forms, and it's important not to get frightened off by something that looks weird. There's something called a torsion balance that actually can exhibit simple harmonic motion. And if it sounds unfamiliar, it's what you figured out when you were a kid and you got on a tire swing and you started to twist yourself up on the swing. Let's take a look at what that looks like. So here's a tire swing, and it's very much like a mass on a spring. If I give it a rotation, you'll see it starts to go back and forth. And basically the torque on it is increasing the farther it turns. The more angle it turns clockwise, the more torque counterclockwise it gets, and vice versa. And it clearly is periodic motion. So, the more you twisted, the more it wanted to untwist. And that sounds like it could possibly be simple harmonic motion. Obviously it would depend on the tire swing, but it would be simple harmonic motion if it fits the same pattern we're used to. So we do our sigma torque is the moment of inertia times angular acceleration, since this is about rotation. So we'd have our tire swing rotating like this. The torque it's going to exert is because it's being twisted. And it will be simple harmonic motion if it tries to untwist itself harder and harder the more you turn it. That would imply that there's some number k, a constant, times theta, the angle through which you've twisted it. I'm putting a negative here because it's a restoring torque instead of a restoring force. And we end up with that equation. So this may look unfamiliar, but the key thing about it is we have theta. The derivative of theta is omega, the angular speed. The derivative of angular speed is angular acceleration. So this is just like we've seen for other types of simple harmonic motion. So with that, we can use our usual equations to try to figure out what this thing's period is. So if we're writing an equation for theta, I'm going to say that it has some amplitude. It's a sinusoidal graph. We'll have our part that converts angle or time into angle times time. If we want the angular velocity, we just take the derivative of this. So the derivative of omega with respect to time, which of course is the second derivative of theta, that's alpha. So we'll solve it like we usually do. We'll plug in theta. Plug in alpha, which of course is just d squared theta dt squared. So anyway, here's the subbed-in equation from the sigma torque equals I alpha. I've plugged in theta, I've plugged in alpha, and as usual we get massive canceling. The trig function and the amplitude cancel. So you solve it around for period, and you end up with this expression here. So you can play this game for anything that starts with sigma f equals ma, where sigma torque equals I alpha, if you can get to a statement like this, theta Rx is proportional to the second derivative of theta Rx, it's simple harmonic motion, no matter how different it looks. If you've got something repetitive, you should ask yourself if it can be expressed like this. Not all periodic motion is simple harmonic motion, but it's a good thing to guess at first and then change your assumption if it's not true.